In this video, we're going to take a look at a component called a reaction quotient. And this will be very similar to the equilibrium expression, except it can be used at any point during a reaction. So if we remember that Kc and Kp are used for equilibrium, concentration, and then pressure, respectively, right? They're used for equilibrium values. The reaction quotient, which is Q, QC, or QP, can be used at any point during the reaction. And if we consider, say, let's do a fairly simple reaction. How about the same one we've been doing the whole time? Yay, our favorite. If we take a look at graphically what this might look like, if we put hydrogen and nitrogen together, say hydrogen is our black line, we've got the pressure of hydrogen here, here's time. Of course, it doesn't react immediately. There's a certain amount of time that takes place as the rate of the reaction happens. We can see that the pressure of nitrogen also decreases over time. And finally, we have the pressure of ammonia. That's going to be increasing until we reach equilibrium. And so kind of once that point happens where they all flatline, they all plateau, this is where equilibrium is established. At this point, once we have established equilibrium, then we can use Kp or Kc. But we may be interested in evaluating what's happening at another point in the reaction. What if we want to look at this particular time point? Well, we can't use K because we're not at equilibrium yet. So we're going to use the reaction quotient, which is Q. And the reaction quotient is the same expression. So for our favorite reaction, how about A plus B turns into C? Actually, we have our reaction. What am I saying? We have our hydrogen and nitrogen. Qp for this would be the pressure of ammonia squared, pressure of hydrogen cubed, and pressure of nitrogen. Same as equilibrium, Kp, right? Qp is the same, mathematically speaking, except it can be used at a different point in the reaction. So Kc can only be used at equilibrium. But Q, the reaction quotient, can be looked at any time. We can look at it initially, especially to determine which way the reaction will go. Say we have 1 atmosphere each of ammonia, hydrogen, and nitrogen. Where will the reaction proceed? If Kp is 0.121. Well, we simply need to analyze Q. If we can calculate Q, we can determine if it's got too many products or too many reactants. Because remember, equilibrium is all about that magic ratio of products to reactants. And so, thankfully, because I've chosen very easy numbers here, if we plug this in, we get Q is 1, thankfully, because I've chosen just 1 atmosphere of everything. We want to compare that with Kp. So our Qp is 1, and in this case we have Qp that's greater than Kp. In this case, remember that this is a ratio of products over reactants. So Qp is too big, right? We want to reach Kp. Kp is our equilibrium. If QP is too big, you have too many products. And that means that products will break down to form reactants. So in this case, the ammonia will start breaking down in order to form more hydrogen and nitrogen. This is what happens when Q is bigger than K. And in that case, then, if we looked at our ice table, we know that we have we can write our reaction again. We can say, okay, well, we know we have 1 atmosphere of everything to start. But now that we know that QP is bigger than KP, that means that we have too many products, so the products are going to start breaking down. That means that we're going to have this one be negative. And again, 2 because it's got the coefficient. And so that means because we're going to be making reactants, we have to put those as positive. And if we were so inclined, we could then solve this for X. We could figure out what the equilibrium concentrations would become. And in fact, we should do that. Why not? So we get 1 minus 2x, 1 plus 3x, 1 plus x. Pain in the butt calculation, but we'll do it. We have, we know that Kp, remember Q will just tell us the direction of the reaction. The Q tells us that the reaction is going to go in reverse, making reactants again. So we have to set up our equilibrium expression. Equals 0.121. So we're going to bust out Wolfram again. Here we go. Let's go ahead and plug all this in. So 1 minus 2x squared divided by 1 plus x. And actually, I'm going to put more parentheses here. That's always one thing in math. We can always have more parentheses. That value times 1 plus 3x, all of that cubed. All right. And all of that equals 0.121. We're going to get out our numbers. So we get, apparently, x equals half. So, miraculously, we get x is 1/2. So, not a good thing, though, because we're going to end up with a concentration of 0 for ammonia. I'm not sure what happened here. Oh, because it got mad at me for the parentheses. I see. So, as we know, these calculators are very sensitive with, there we go, we've got some values. So, as before, we have 2 imaginary values, we have a negative value, but we have 1 positive value. That's the one we're looking for. So, x is equal to 0.16125. There's your lesson. Don't forget your parentheses. Make sure that all your syntax is correct. So now we know that nitrogen is 1 plus 0.16 is going to be 1.16 atmospheres. For hydrogen, it's 1 plus 3 times 0.161, which is 1.48, I'm assuming. And then the ammonia, which will be 1 minus 2 times 0.161, which will be 0. Okay, forget it, I'm not going to try. 1 minus 2 times 0.161. What? 1 minus 2 divided by times. 1 minus 2 times 0.161. You get 0.678 atmospheres. So there we have it. We have our equilibrium concentrations now. Again, this is not something we will know. We have to know which one is going to have our negative x, which one's going to have our positive x. And that comes from Q. For example, if we take a look at another example, let's say now we have 10 atmospheres of ammonia, we have 15 atmospheres of hydrogen and 8 atmospheres of nitrogen. We can see what Q is going to be. Q is ammonia squared, hydrogen cubed, and nitrogen. So let's hope this works out. So we have 100 divided by 15 cubed divided by 8. We get 0.0037. That tells us, in this case, Q is less than K, which means that the reaction proceeds forward. So that means that in our ICE table, and this time we're not going to bother calculating it, but we can go ahead and put all of our values. In this case, we're going to be subtracting our reactants and producing products. That's the point of doing Q. We need to know which one is going to be losing stuff, which one's going to be gaining stuff. So if Q is less than K, we're going to be going in the forward direction, meaning we're consuming reactants. So reactants will have the negative X, and we're making products, so products will have the positive X. And then you can go ahead and solve this if you are so inclined afterwards. Lastly, if by chance, that means that the system is already at equilibrium, if we have them equal to each other. Remember, Q can be done at any time. K is only for equilibrium. And so, if they are already equal to each other, we're already at equilibrium. If QC is greater than K, or I'll just say Q is greater than K, could be either C or P. That means that the reactants, we have too many products, so products break down. And so the products will get the minus X, whatever they happen to be. In this reaction, we had a coefficient of 2, so we had minus 2X. If Q is less than K, then the reactants get consumed. And therefore, the reactants get the negative X. And then the products get the positive one. So with that, that's our conclusion of using the reaction quotient to determine the direction of equilibrium, so you can figure out how the concentrations are going to change in order to reach equilibrium. And from there, you can then calculate what the actual equilibrium concentrations are, or pressures.